Welcome you all to another session on machine learning in our practitioner's course on analytics. We talked about different types of machine learning algorithms, the philosophy, the tricks, the traps. Let us now get into a quick crash course of the most important form of machine learning, or rather the most widely used form of machine learning, which is called the classification based algorithms. So, classification, just to quickly remind you, is all about classifying, as the word says. So, in a normal regression, our goal is to predict a particular value of the output. In this case, we want to categorize the output. So, for example, let us take case of a bank. So, this is one of the most popular uses of classification based machine learning algorithm. So, a bank wants to classify its customers into defaulters and non-defaulters. So, a bank is in the business of giving loans. It wants to predict which customers can default, which customers have less likelihood to default. So, this is a classic or a very popular case of classification based algorithm. There can be similar, for example, if you talk about medicine. So, based on the different parameters, different vital statistics of a patient, you want to predict whether the patient has a particular disease or not disease. So, these are typically binary classification. You label them as 1 0 or 0 1 depending upon your convenience. There can also be cases where you want to break them into multiple categories. So, for example, you may want to, based upon the, say in case of HR, based upon the different characteristics, different kinds of scores, you want to see to predict whether a person would be a low performer, high performer or a mediocre performer. In this particular case, you can also use a regression, but often this categorization can give you slightly better results, or based upon different kinds of characteristics, it wants to see whether a person is a better fit for finance, marketing or operations. So, what fits his profile better in terms of his potential performance. So, these kind of problems where the output variable is not a continuous variable, it is a category. So, these are the problems which come into the classification set of algorithms. There are several methods. Some of the most popular used methods are something called logistic regression, which is extension of the same principles as of normal regression or linear regression, multivariate regression or bivariate, into problems where you have to get them into different categories. Then there are these simpler but yet very powerful approaches, naive Bayes, and an extension of naive Bayes is what is generally called linear discriminant analysis based algorithms. And then you have the very classic or very intuitive k nearest neighbors based methods. So, let us have a quick look on each of these methods and then also understand what are the pitfalls, get into a bit detail of it. So, let us start with what I mentioned at very last, k nearest neighbors. Now, this is the most I would say intuitive or most natural way in which we also try to classify people around us or various things around us. So, what it says is, the popular proverb that a man is known by the company he keeps. So basically what you do is, let us say draw two parameters, let this one be x1, this one be x2, let these be any two parameters. For example, if we are talking of a default, let maybe x1 is a parameter like his past payment record, whether he pays on time or not. X2 may be his account balance. So let us not bother about what these exactly are, because depending on the problem these will vary. And then, for example, we know certain people defaulted, certain did not default. So let us put the defaults as, let us classify them as n, let us mark them as n. So for example, I am just drawing, so let these are the some points, some people who did not default. And let us assume that these are people who defaulted. So now for example, assume that you get a new data point. So you got a data point here, for example. Let this be a data point. So you want to predict whether this fellow is he a defaulter or a non-defaulter. So what k nearest neighbor says is that look at the people who are around him, who are the closest people around him. So you can very easily say that if I choose his closest neighbor, probably this fellow is the closest neighbor. If I choose two closest neighbor, then probably this and these two are closest neighbor. So this may be a neighbor, this may be a neighbor. If I have to choose three neighbors, these three may be neighbors. If I have to choose four neighbors, then this fellow also becomes a neighbor. So if I decide that okay, I make a rule that I will classify a person as per his closest neighbor. In that case, I'll choose this fellow and say that this record is a non-defaulter. However, if I say I will choose two closest neighbors, again for 1 he is a non-defaulter, for 2 he is a non-defaulter. If I choose 3, again he is a non-defaulter. If I choose 4 points, then 3 points say that he is a non-defaulter, 1 point says he is a defaulter. You do a majority vote and then you still say that he is a non-defaulter. Similarly, if I had another point which was somewhere here, in this case probably if this was the closest fellow, then we would say he is a defaulter. If next closest was this, then among the two, then it's kind of equal, you are in a tie. If you choose 3 points, then probably again this fellow breaks the tie. If you choose 4 points, then again it's a tie. So what we are doing in a way is that we are polling how many of the nearest neighbors are defaulters or non-defaulters, and we go by the majority vote. So typically very intuitive, and it works perfectly fine in many simple cases. In fact, a lot of the machine learning algorithms which are used in many recommendation based systems, in shopping carts and even some sentiment based analysis, they do this k nearest neighbor methods. And if you look at the results also, surprisingly the results come out to be really good in many cases. In fact, they beat some of the most advanced algorithms. But there are few riders. The first rider is that this is very subject to, it's a function of the, it is subject to choice of k. K means the number of neighbors that you choose to make the decision. And if you look at a typical profile, if I have to make a graph out here, so let me plot error out here, the mistakes I make if I classify using this. Let me put 1 by k here. So 1 by k here means that as k increases, I am going close to the origin. So the furthermost points are those, the lowest can be 1. So maybe this extreme is 1 and other values are beneath it. And if we plot it, we see the plot is something like that. So as you increase the number of k's, if you increase, so somewhere between this to this, you find that you get the least error. And beyond it, if you take more number of neighbors, then what happens is typically it is almost sampling the entire data set, and hence your accuracy reduces. In the initial part, if you choose less number of k, then what happens is that the nearest neighbor becomes a very strong influencer. So if there have been some odd points here and there, in that case you may still get error. So what happens is there is an optimal typically range between which it works beautiful in most cases. So typically it's a thumb rule that if k is between 5 and 10, then it works good. If it is below this, then the model becomes slightly unstable. The variance is high. If I have to talk in terms of the bias variance discussion we had last time, it is too much adapted to the data set. On a new data, it may not work fine. If k is, this is when k is low. When k is high, then bias increases. So in a way you are sampling the entire data set and hence your accuracy reduces. So keep in mind that it is very much subject to, and sometimes when the data set is slightly more complex, the k nearest neighbor may not also work very great. So you have to keep in mind the between 5 to 10, yes, typically it works good, but there is another rider along with it, and that is the curse of dimensionality. So when the number of parameters, in this case we had worked with only 2 parameters, but if when number of parameters, I mean x1, x2, xn. So if n is large, then it can be shown that most data points in an n-dimensional cube. So if we assume that all data points are part of a cube, so a 3 dimension is like this is x1, x2, x3. So if I make an n-dimensional and I try to plot, and if that be considered kind of a cube, so most data points in a n-dimensional cube tend to be far apart. So what happens is it becomes very difficult to find a close neighbor. So what happens is most of the points are actually very much far apart from each other, and because they are very far apart from each other, the entire notion of having k nearest neighbors does not make much sense. So, it is like you are being in Kanpur and your closest neighbor is in, say, Norway, the other closest neighbor is in Australia. So, Australia and Norway itself are so far away from Kanpur that does not make sense to even call them as neighbors. But yeah, from a technical standpoint, yes, you can still come out with some results, but they are not actually a neighbor in the strictest sense. So, if you have, unless you have very huge number of data points, typically finding these neighbors and actually classifying them as neighbor itself becomes a question mark. So, for when the number of parameters is large, because they tend to be far apart, it means that k nearest methods are unstable. So, you do not use these methods in this case. So, typically what you do is, when you use these methods, we should also consider what is called error rates. So, when you use these methods, there are always misclassifications that happen. So, there will be data points for which your model will classify them wrongly. So, what you do is you calculate a metric which is so, do not be scared about this complex term. So, I is like it is a very commonly used variable in probability based methods. It is called an indicator variable. So, what happens is, this I takes a value of 1 if yi not equal to yi cap. So, what happens is, this yi cap, so cap, as we discussed earlier, it means your prediction. So, you predicted that something is 1, but actually it was predicted as 0. So, 1 and 0 being two different categories. So, if it fails to predict, I gets a value of 1. If it correctly predicts, I gets a value of 0. So, in this case, what happens is, basically what you are trying to do is, you are trying to sum up all the number of wrong predictions you made and you divide by the total number of predictions that you made. So, n is the total number of data points. So, this gives you an average error rate, and your goal is to minimize this error rate. So, if you see that in k nearest neighbor, when the number of dimensions is very high, the p, number of parameters, if high, k nearest is not recommended. So, typically in any classification algorithm that you use, you calculate this error rate, you calculate this formula. If you are using a software, it will itself do the calculation, it will give you these kind of estimates, and your goal is to reduce it. So, what we find is that if for k nearest neighbor, this does not give a very great result. The other simple method, which is again very popular, is naive Bayes classifier. So, if you recall your study of probability in class 12, recall there was this Bayes formula. So, Bayes formula for conditional probability. So actually the formula is not a very complex formula. Let me just give you a quick refresher. You don't even have to remember. Many people try to remember this formula. Actually you don't have to remember. So what it says is that for example, what is the probability of P A and B both happening? So you can say that this is the probability of P A happening, and once P A has happened, probability of B happening given that A has happened. So this slash A means that given that A has happened, happening of B. So probability of both P A and B happening, you can easily say that it means that the probability of A happening, and once that A has happened, probability of B happening. But then you can also swap A and B, right? So this is also same as P A by B. So if you compare these two formula, what we basically get is that P A into P B by A is equal to P B into P A by B. Now Bayes theorem is nothing but a rearrangement of this basic equation, or in other words, simple terms, P B by A is equal to P B into P A by B by P A. So probability of an event B happening given that A has happened is nothing but probability of the event happening irrespective of whether A has happened into probability of A given that B has happened divided by the total probability of A happening. So if you remember this equation, this becomes easy to derive, and this is what is called Bayes formula or Bayes theorem. And in modern analytics, this very simple but very intuitive, or I would say very insightful formula is the basis of lot of machine learning algorithms. In fact, there is an entire field of Bayesian statistics which primarily works on this formula. How it works, let me just give you a brief insight, and then you will understand that why naive Bayes classifier becomes a very attractive tool. In fact, apart from K nearest neighbor, this is one of the most popular tools for most of the recommendation engines that you would come across online. So let us have some brief discussion on this. So let me write this formula again for you. So basically we said that P A by B is equal to, let me put it in a more ordered way, divided by PB. So what we are doing is, if you notice this term and this term, it gives a way of swapping A and B. So moving from probability of B given that A has happened to moving to probability of A given that B has happened. Now in case of analytics, many a times what happens is, now if you look, this A was your original estimate of probability of A happening. So if you consider B to be an information or a new data received. So what it says is that given that you receive a new data point, or maybe let me call it D so that it's easy to visualize. So, given that a new data point that you received, the probability, so this was PA was your prior probability, this is called a prior. Now, D by A is that given that A is the situation, what is the probability that you could get this new data in the first place? So, what you find is that, and if you divide that by the probability of getting this data irrespective of whether you got A or you did not get A. So, you find that if A be the, if PA be the probability of an event A happening, this formula gives you a way to adjust that probability given that a new data point has received. So, given that you now got new information, new data point, you revise your estimate of A. So, the probability of A now, so what happens typically is that, and the reason it becomes so powerful in analytics is that what you do is you start with some, in a typical case you start with some assumption about this probability of A, whatever be the value. And then you say you have received, so you take first data point, you say that what is the probability of I getting this data point given that A has happened, you multiply by this, do this calculation. I will not get into the further details of into this because it is a field in itself, but what happens is after that you, after that iteration you get a revised probability of A. Now, in the next step you again put this value here, again get the new data and again revise your estimate. So, after some time, some iterations that you do, in a way simulations that you do, you get a stable value of probability of A given that all the data that you have received. So, this is the way a lot of classifications happen. For example, if you are deciding whether who will win an election, so given that a new data point receives you, you keep refining your probability of A winning, A being say a candidate winning, the probability of a candidate winning. Based on new data you keep refining, ultimately the model comes to a stable state and you come to your prediction. So, that is what this Bayes theorem is about. Now, if you recall here, this actually this PA, now what happens is that this PB is actually probability of B by A into PA plus probability of B given that A complement into PA complement. Now, in reality a lot of these calculations become complex, especially if there are multiple parameters. So, what you do is you make certain assumptions, simplify those calculations and then use this Bayes theorem. So, let us take for an example a case of spam handling. In email. So, say for example, you get a lot of mails, some mails are spams, the mails which are not spams they are called hams, that is just a lingo. Suppose you got one objectionable word, for example, let the word be virus. So, basically you make a rule, or you know that if a word virus comes in the mail, then there is a high probability of the mail being spam. So, there can be other words also. So, for example, you do an analysis and finally you based upon your review you found you make a matrix of presence of word virus versus not presence of virus and a mail being spam or not spam. So, for example, you make this table and so for example, there were 4 cases when the word spam was present and word virus was present and it was a spam mail, and there were 16 cases when the word virus was not present yet it was a spam. So, And similarly, there was one case when the word virus was present, but it was not a spam. And there were 79 cases when word virus was not present and it was also not a spam, it was a ham. So let this be this. So we have 100 points, we have around 95 points here, and we have 5 points here. So this is what it looks like. So what you do is you calculate the likelihood based upon this of something being a spam or not spam. So you try to calculate likelihood out of this. So how you do is very simple. You just divide these by, so if I have to convert this into a likelihood table, so the table would look something like this. So you had 20 points here, you had 80 here, this was 100. So you divide each of them by this 20, so this becomes 4 by 20, this becomes 16 by 20, this becomes 1 by 80, this becomes 79 by 80, this becomes 5 by 100, this becomes 95 by 100. So this becomes your likelihood table. Now what you do is, the trick that you do is, you say probability of something being a spam given that the word virus came is equal to probability of word virus given that it's a spam into probability of it being spam by probability of the word virus. So note this term this is your likelihood. So what we are calculating is here is that probability of some being virus given that it's a spam. So you know that from here. This is the prior probability of something being a spam. So in this case you know that the prior probability was 20 by 100. So that is the prior probability, and you know the probability of something being virus was 5 by 100. So in a way you calculate this, you can easily calculate this probability. So what naive Bayes theorem does is something more. So here it was a simple case of just one word virus. Now assume that there are many other words that you took. So for example, apart from virus, maybe there is another word, common word, Viagra for example, then there may be some other word, prize. So you may have these kind of tables, or you can have another word like money. So in a way you have a bigger table. Let me just try to draw that table for you, and then we will understand it slightly better. So let us just have 4 words to begin with. Let this be word 1, whatever be the word. It may be Viagra, it may be grocery, it may be price, it may be money, it may be virus. So these are the 4 words, and maybe let me, for sake of clarity, make the divider with a double line. So, this is yes, no, yes, no, yes, no, yes, no, and this being spam, this being a ham. So, for each of them you have some values here, you have some in this case, for example, for this we knew it was like 4 by 20, 1 by 80, 16 by 20, and it was 79 by 80. So, similarly, based upon the sample that you have taken, you have this filled. Now, the probability, and for example, a case came where this was yes, this was no. You got a mail where this particular first word was present, the second word was not present, the third word was not present, fourth word was present. So, the probability of it being a spam, given that first word was present and second word was not present. So, let me just put it by a complement, which is a horizontal line over this, and word 3 was also not present and word 4 was present. This by Bayes theorem is nothing but probability of given that it is a spam into probability of something being a spam divided by probability of now. Notice from this particular table, you can actually calculate all the permutations, combinations, and then because you know each of these. So, P W1 and W2, which means you know this part and then this part and this part, you know. So, you can actually calculate and do this. It is a simple algebraic exercise that you would have done in your class 12. So, this is the way the naive Bayes is used. However, what happens is that this calculation of this actually, in this case we had just 4 examples. So, maybe you can just do some kind of a manipulation, but this wherever you will do, if you do by and that is why it is called, there is this, notice this word naive. Naive means very simple. So, what happens is we unconsciously make an assumption that this W1, W2, W3, W4 are independent. In reality, this independence may not be there. So, what happens is in reality, this particular formula, this particular term, this and this. So, they are very, very difficult to compute because there may be relations between W1 and W2. So, it is like saying that if a male has W1, the probability of W2 also happening is influenced by this. So, they are not actually independent. So, what happens is in naive Bayes theorem, you simply assume that they are independent. The moment you assume they are independent, then you know that P A intersection B for independent events is nothing but PA into PV. So, in this case, for example, moment you assume them to be independent, all you do is you replace this by something P W1 given it is a spam into P W naught 2 given it is a spam multiplied by W naught 3 given that it's a spam multiplied by W4 given it's not a spam. So, you simply replace that by a product. Similarly, you replace the denominator also by a product, and then it's a matter of simple calculation. So, what happens is you do this calculation, and for each of these combinations, for example, you start filling the numbers and you find out that the probability of it being a spam, given that W1 happened and W2 did not happen and W3 did not happen and W4. You calculate this value, it comes to some number. Similarly, you calculate the value of ham. You do the same exercise again, that what is the probability that it was not a spam for the same thing. You do a calculation of this, whichever is greater. If this is greater than this, then you classify it as a ham. If this is greater than this, you classify it as a spam. So, in reality, what you do is this value actually does not strictly. So, what happens is in a smart case, you notice whether you are calculating spam or you are calculating ham, this value actually does not matter. This is constant. It does not have any term of spam or ham. So, in general, what happens is you simply ignore this. Simply ignore. The moment you ignore, all you have to do is you have to just calculate this numerator. So, what happens in a calculation is that instead of probability, you in a way calculate the likelihood, just the numerator. Similarly, likelihood, you simply calculate the numerator, and to convert it, so if this PS or LS, if this be LS and this be LH, then what you do is probability of spam is equal to LS by LS plus LH, probability of ham is equal to LH by LS plus LH. So, you calculate this and then you are done. Now, one of the issues that comes here is that you have assumed that these are all independent. In reality, this independence does not hold good. The other concern that happens is you took 4 words, suppose tomorrow 5 new words got added, and then you got these are like completely new words for which you do not have any data point. So, in those cases what happens is that some of these terms may actually have 0. So, if these are 0 and you are multiplying, so this term actually becomes 0. So, you get actually after doing all this calculation, these values simply because a term did not exist, it becomes 0. So, what you do is there is something called Laplace estimator, which is nothing but you say that I will not allow 0 to happen. You make sure that it is never 0, it is minimum of 1 and any value, 1 by 1 divided by total values and something else. So, you make sure it is always non-zero. So, if it is non-zero, then calculation becomes simple. So, this is in summary the naive Bayes. Now, in naive Bayes we assumed, let us be very clear, assumed independence of W1, W2, W3, Wn. Now, this is a part of a more generic algorithm set called linear discriminant analysis. In linear discriminant analysis, what you do is that you do not necessarily assume independence, and what you do is this this prior, you assume it to be a Gaussian or a normal distribution, and then it is a complicated formula. So, what happens is the output is also comes out to be a Gaussian, and then terms comes out to be a linear equation. So, that is something called linear discriminant analysis. You make more complex assumptions about the nature of probability distributions. You have something called quadratic discriminant analysis. So, these are different methods which are used. However, the naive Bayes is computationally very efficient, very simple, and for most cases it kind of suffices. But let us be very clear that because it assumes independence, it also assumes that every factor is equally important. So, what happens is that if you take too many factors and your problem designer has been kind of too finicky about it, your models tend to get very unstable, because there are too many factors. Suppose instead of these words, I would have instead of phrases, he would have broken even the phrases into words, and he would have chosen every hundreds of words, then it would have become very complex. And also these are like good if the data is largely categorical, in case presence or non-presence of words. If it was numeric variables, then it would have problems. Then you would have to break those numerical variables into different. So, for example, instead of presence or non-presence of word, we had something like count of words or length of email. In that case, you would have to split these lengths and counts into low, medium, high different categories and then try to use, and you find that the algorithm then does not work very great. So, but it is, you need to be very clear that it is very fast, it is simple, and I would say also effective in many fuzzy cases. Fuzzy in the sense when the data is also not very clear, accurate, it turns out to be very accurate. Also, training is quick. You do one basic sampling of your emails and it can smartly train itself. And also, if the data is noisy or there are a lot of missing values, with Laplace estimation, it tends to work pretty well. So, and that is the reason that for many online applications, they use naive Bayes or one of its modifications. For example, your recommendation engines in most of these shopping e-commerce sites, etc., all likelihood are going to be naive Bayes. based methods. Okay. So now let us move to a more serious method. Naive Bayes is also serious. I am not saying it is not serious, but something which is used a lot in enterprise based situations, very popular. In fact, if you talk in terms of its usage, then it is probably more applied or more widely used than even linear regression, and this is the logistic regression. So in logistic regression is nothing but your linear regression was nothing but a0 plus a1 x1 plus a2 x2 up to an xn, where these a0, a1, a2, these could be either, or these x1s rather, these x1s, they could be either continuous variables or dummy categorical variables, and y was a continuous variable. What if I want y to be a discrete variable or rather a categorical variable? I want finally the answer to come as something like a 0 or 1. So mostly logistic regression is used for binary classification. There are extensions of logistic regression for non-binary or multinomial classifications, but they are not very popular. The most popular use is for binary classification. So in this case, what you do is there is something called a logistic function. So logistic function so I am assuming I am starting with simple case of just one single variable logistic regression, and the same thing extends to multivariable. So this is the function. So if you swap, do some elementary algebra, you will find that px by 1 minus px is equal to e to the power p0 plus b1x. If you take log of both sides, natural log, will find log of px by 1 minus px is equal to beta 0 plus beta 1x. So this particular term is called a log odds or logit function. So this term, if you now note, is almost same as that of linear regression. The y term is slightly different. Now what you try to do, because it's a classification algorithm, now this is kind of a log odd, like if you just roughly think that this p be a kind of a probability, it is kind of a log of something happening versus something not happening, that comparative ratio. So what in this case we do is we try to actually maximize something called a likelihood function. So this is how the mathematical form is evolved. So which is nothing but so this is basically a symbol for product. So we all know sigma mi is symbolizes sum, this symbolizes product. So what it is trying to do is it is calculating the parameters for which this is called likelihood. it tries to find those parameters for different betas that maximizes this particular probability. So, this is called a set of methods called maximum likelihood estimator methods. So, maximum likelihood estimators. So, similarly, if you were doing in this case, if it was you were doing this was for a bivariate case, if you are having multiple variables, the same function would look something like log of px by log of 1 minus px is equal to beta 0 plus beta 1 x plus beta n xn, and the same formula that comes. So, here what happens after you have done this thing, it comes with a value, you convert that value into a probability, and if the probability is greater than 0.5, you say it belongs to a class 1, if it is less than 0.5, it belongs to class 0. So, thank you very much. We will continue this further and then take ahead from there. Thank you very much.